Have you ever stopped to think about how we make things, well, really, really small? Like the powders that become cement or the advanced materials that make up new technologies? Well, a lot of the time, the answer lies inside one of the most powerful and, deceptively simple machines in all of modern industry. Today, we're cracking open the secrets of the ball mill. I mean, just look at the size of this thing. These huge, rotating drums are the absolute workhorses of so many industries, from mining all the way to pharmaceuticals. At the end of the day, they're basically giant high-tech grinders. So yeah, what exactly is going on in there? Let's dive in and find out how this machine, which looks pretty simple on the outside, is actually a cornerstone of industry. It's capable of everything from just crushing rock to literally crafting the building blocks of nanotechnology. To really get what a ball mill is all about, we gotta look past that massive steel shell and see the pretty elegant physics at play inside. It's this amazing mix of raw power and really precise science. At its heart, the idea is incredibly simple. You take a big drum, you put your material inside with a bunch of heavy balls made of steel or ceramic, and then you spin it. But the real magic is how that spinning action actually breaks stuff down, and it all comes down to two key forces. So on one hand, you've got impact. That's just the raw, crushing force of these heavy balls falling and smashing into the material. But on the other hand, you have attrition. This is more of a grinding, shearing force, right? It happens as the balls and the material all rub against each other and the wall of the mill. The genius of the whole system is being able to control which one of those forces is doing the most work. And check this out. This cutaway shows you that it's not just one big empty can. These industrial mills are often split into different compartments. You can see the first section has these bigger balls for coarse grinding, then there's a divider, a diaphragm, and the second section has smaller balls for that super fine grinding. It's such a clever design. You get a multi-stage, super efficient process all happening inside one single machine. Okay, so how do you control whether you're smashing or grinding? Well, the single most important variable by a long shot is speed, the speed of rotation. And this is where the simple machine becomes a really precise science. First, we've got to talk about a really key concept, critical speed. See, if you spin the mill way too fast, centrifugal force just takes over. It pins the balls and the material right to the wall, kind of like your clothes in a spin cycle. And when that happens, nothing gets ground. So running at critical speed is totally useless, but running relative to it, that is everything. And this is where it gets really cool. This shows the two main ways it works, and it's all about speed. At lower speeds, you get what's called a cascading action. The balls just kind of tumble gently over one another, creating all that friction and shear we talked about. Perfect for fine grinding. It's kind of like using a mortar and pestle. But if you crank up the speed, you get cataracting. Now the balls are actually being thrown up into the air and then crashing down, creating these huge high-energy impacts. That's more like breaking rocks with a hammer. So that's the big takeaway, right? It's not just about spinning faster for the sake of it. It's about using speed to precisely control the type of force you're applying. And that control is what turns this thing from just a simple crusher into a genuine precision instrument. But hold on, speed is just one piece of the puzzle. To really master this whole process, especially when you're trying to create some super advanced materials, engineers have a whole dashboard of other dials they can turn. I mean, they can change the milling time. We're talking hours, sometimes even days. They can swap out the size and the density of the grinding balls themselves. They adjust how full the mill is, and this one is critical, the ball-to-powder ratio, or BPR. Fine-tuning this whole system is how you go from just making concrete dust to actually engineering brand new materials at the nanoscale. And this chart is a perfect example of that fine-tuning in action. So researchers were trying to shrink a material's crystallite size. That's the size of the tiny crystal structures inside the powder. They tested different ball-to-powder ratios, and look what happened. A ratio of 40:1 gave them the smallest crystal size. But when they went higher, to 50:1, the result actually got worse. They found the sweet spot. And that's the whole game, really. It's all about finding the right balance. If your ratio is too low, you just don't get enough collisions to do the job. But as this quote points out, if you go too high, you create another problem. You can actually end up cushioning the impacts, or the balls just don't have enough room to move and build up energy. It's all about hitting that perfect ratio for maximum efficiency. And here, wow, here is the incredible result of all that optimization. On the left, you've got the raw magnesium powders, all spherical and separate before they go in. But on the right, After 18 hours of milling under those perfectly controlled conditions, that structure is totally transformed into this tightly packed nanocrystalline material. Just an amazing difference. The final green size they achieved was just 60 to 80 nanometers. Now, to put that into perspective for you, that is over 1,000 times smaller than the width of a single human hair. That's an absolutely mind-boggling transformation, and it's all driven by controlled mechanical force. So, you might be asking, why go to all this trouble? Well, because when you create materials with a structure like this at the nanoscale, you unlock incredible new properties. These specific powders, for example, are being developed for biodegradable medical implants. We're talking screws or plates that can hold a bone together while it heals and then just safely dissolve into the body. No need for a second surgery to remove them. How cool is that?
Okay, so this all sounds amazing, right? But as powerful as this technique is, that brute force nature, it isn't without its downsides. There are some real inherent trade-offs that come with the territory. For starters, all that constant impact and grinding wears down the media, the balls themselves, and that can actually contaminate your final product. The intense energy can also damage the material structure, a process called amorphization, where it loses its perfect crystal order. You can also get particles that cold weld themselves together, or just end up with a wide variety of particle sizes instead of a uniform result. And of course, spinning these giant, heavy drums, well, that takes a ton of energy. So it really boils down to this. The core trade-off with ball milling is that you're sacrificing a certain amount of precision and purity in exchange for incredible power, versatility, and pretty low costs. It's a fantastic, powerful tool, but you always have to be aware of its limits. Which really brings us full circle, doesn't it? This technology, which is more than 100 years old, was born from this very basic need to just crush rocks to make cement. And yet today, because we now understand the physics behind it so well, it's become this absolutely essential tool on the cutting edge of science, creating the literal building blocks for nanotechnology. And that kind of leaves us with a fascinating thought, In our modern age of super delicate, high-precision technology, one of our best methods for building the future is still, at its very heart, a really, really smart way of just smashing things together. Maybe sometimes the most elegant solution really is just brute force, applied perfectly.